Nowadays, when we divide larger numbers, we generally use a calculator. For smaller numbers, we either have them memorized or we use a calculator as well. Now, not all numbers can fit on our calculator, and if we happen to forget our calculator, we might have to do it by hand. In this case, rather than doing the whole thing by long division, just wind up with some long decimal place, it is helpful to check ahead of time to see if a number is actually divisible by another number. For this, we have some nice tricks that we can use. Before we get on to our nice tricks, we need to look into some terminology, such as the remainder. The remainder is if we take a number, such as 15, divide it by 7, and divide it by another number, such as 7, we get what's left over is our remainder. So 15 divided by 7, 7 goes into 15 2 times, and then we have 1 left over, which happens to be our remainder. When looking for the remainder of a number A divided by another number B, we will use the mod operator. For example, 15 divided by 7 would be when trying to find the remainder would be written like this. 15 mod 7 equals 1. So the remainder of 15 divided by 7 is 1. So some final helpful rules when creating our tricks for finding divisibility. First off, if we have a sum that we're looking for the remainder of, we can then break that sum apart, find the remainder of each part, sum them together, and then take the remainder of that. We then have a multiplication equivalent, and we'll be using these throughout in order to help break down our problems into more manageable chunks. Let's start off with divisibility by 2. First off, we have our integer a. We then break it down into each of its base 10 components. So our ones digit is being multiplied by 1, our tens digit is being added to that and being multiplied by 10, our 100 digit is being multiplied by 100 and then being added, and so forth. We then can note that 10 is divisible by 2, as 10 divided by 2 is 5. Since the remainder of a divisible number is 0, we can then substitute 0 in for all of our 10s, as 10 is divisible by 2. We then simplify and add that 0 to our ones digit, giving us just finding the remainder of the ones digit. So our first rule for divisibility by 2 is the first digit divisible by 2. If so, it's divisible by 2. For example, 248. 8 divided by 2 is 4, so 248 is divisible by 2. Now, divisibility by 3. Start off at the same spot, separating our number a into a series of digits. We note that 10 mod 3 is 1, giving us a remainder. So as you can see here on the side, so we can substitute all of our 10s in with 1s. We then simplify, giving us the sum of our digits. So for our rule for 3, we check the digit sum for divisibility by 3. For example, 567. 5 plus 6 plus 7 equals 18, which happens to be divisible by 3. Thus, 567 is divisible by 3. For divisibility by 4, we start off same spot as always, separating it down to our base 10 digits. There, we note that 100 is divisible by 4, so we can replace all 100s with zeros. Then, we simplify, giving us our ones digit and our tens digit. So, for our rule, we check if the first two digits are divisible by 4. For example, 936. 36 divided by 4 is 9. So, since 36 is divisible by 4, 936 also is divisible by 4. For divisibility by 5, we start at the same spot. we note that 10 is divisible by 5. From there, we can just replace all 10s with zeros. Then we just are left with our ones digit. So we just check to see if for our rule, we just check to see if the first digit is divisible by 5. So for example, or which is equivalent of saying the first digit is a 0 or a 5. So for example, for our number 1,230,975, since the last digit is a 5, 1,230,975 is divisible by 5. For divisibility by 6, we note that 2 times 3 equals 6. So if we have our number divided by 6, we can break this down and check each case individually. So we check divisibility by 3 and divisibility by 2. And that is our rule. For divisibility by 7, this is by far the most complex divisibility rule. I had to wind up looking this up on Wikipedia, though I did create though I did derive it on my own. So again, we start by breaking our number into its base 10 form. But unlike the other occasions, we're not going straight to finding the remainder. We're going to multiply it by 5. Why we can do this is since 5 and 7 share no common factors aside from 1, no matter how many times we multiply this 5, whether or not it's divisible by 7 will not change. Why we are doing this? It will make a step later on a lot easier. How do I know it will make it a lot easier? I worked it out on the side. That will also take a while, so I have to sadly leave it out of the video. If you are interested in this sort of thing, and why I can multiply it by 5, and why it's necessary to do so, I would recommend it looking into number theory, which is a super interesting field, and I probably shouldn't go on more about that. So, then start off where we normally do, except for everything is being multiplied by 5. There, we can then take out a 10 from the, so we're going to pull out a 10 from all digits 10 and up, and of course we're going to pull out 5 from everything. We then note that 50 mod 7 is 1, so we can replace our 50 with a 1, giving us 5 times the first digit plus the other digits divided by 10. And we can also note, for further simplification purposes, 5 mod 7 equals 5, and so is negative 2 mod 7. So we can then substitute out, since we're still taking the remainder regardless, a negative 2 for the 5, thus giving us our the tens digit and up divided by 10 minus 2 times the first digit, and then you find the remainder of that. And that happens to be our rule. So double the last digit and subtract it from the remaining part of the number. For example, 225. 52, which is our last 2 digits, minus our first digit, 5 times 2, gives us 52 minus 10, which equals 42, which happens to be divisible by 7. Thus, 525 is divisible by 7. For divisibility by 8, it goes similar to 4 and 2. So we have our number A, we separate it out into its 10-digit form, into our base 10 form. We note that 1,000 is divisible by 8. We substitute 0 in for the thousands, for all our thousands. We then simplify, and that gives us our rule. We check if the first 3 digits are divisible by 8. This is the clunkiest of the rules, in my opinion, even clunkier than 7, despite its longer proof. And so, for example, 59,232. 232 is divided by 8 is 29. So 232 is divisible by 8, thus 59,232 also is divisible by 8. For divisibility by 9, this one's similar to divisibility by 3. So we start off like we normally do. We note that 10 mod 9 is 1. We then substitute 1 in for all of our 10s, giving us the digit sum. So for our rule, we look at the sum of the digits and check for divisibility by 9. So for example, our number 12,345,987,654. We sum the digits. This gives us 54, which is divisible by 9. Thus, we note that 12,345,987,645 is also divisible by 9. For divisibility by 10, similar to 6, we just check for, we can break it down, and then we check for divisibility by 2 or 5, or if we just see if it ends in a 0. For divisibility by 11, which happens to be the last rule we will be going over, we start off similar to normal. Then we break it down and expand our exponents. We note that -1 mod 11 equals 10, and so we can then substitute -1 in for all of our 10s. This gives us the alternating sum. So we alternate between adding and subtracting digits, and we check to see if the final sum is divisible by 11. This gives us, so for example, our number 12,344,321. We alternate the digits, and that gives us 0. 0 is divisible by 11. Thus, 12,344,321 is also divisible by 11. Now, for a quick recap. For 2, we just check if the last digit is divisible by 2, which means it's even. For divisible by 3, we check if the digit sum is also divisible by 3. For 4, we check the last two digits and see if they are divisible by 4. For 5, we check the last digit and see if it is 0 or a 5. For 6, we just check for divisibility by 2 or 3. For 7, we subtract twice the last digit from other digits. For 8, we check the last 3 digits to see if they're divisible by 8. For 9, we check the digit sum for divisibility by 9. For 10, we check if it ends in a 0. For 11, we check if the alternating sum is divisible by 11. So for one last note, for clunkier rules like 7 and 3 and 9 to an extent, you can repeatedly apply this rule. So while you might not see, so if you have a 10-digit number, you might not see much progress after using the rule for 7 once, but after maybe using it 5, 6, 7, 8 times, maybe 9 or 10, it will be much more visible, and you could even check it by hand rather than simply shrinking it down to something more manageable for a calculator. In terms of sources, for the 7 rule, as I may have mentioned earlier, I did look at Wikipedia for checking the rule, though I did derive the formula for it on my own. I will be posting a link to the Wikipedia article, which has divisibility rules 2 through 30, hopefully in the description below. Thank you.